Or we can start from the top again. Welcome Zoom, thank you for your patience, thank you all here. So today we'll be presenting a preliminary study of the Alluvial Aquifer here in Oakridge, Oregon. And to begin, I'm just going to detail our journey through our field course, and which also mirrors our presentation. And that begins with the regional and site geology. So we began by setting the stage and looking up all of the background that we needed, and then we're able to go out and look at some of the water cycle, and we had some help from the USGS to go around the area and get acquainted with the surrounding, which then helped us lead into our methods and approach, where we laid out a plan and took a multifaceted, multidisciplinary approach into looking at this aquifer. So part of those methods involved ground penetrating radar, which is a geophysical approach, and then using some pumping tests to examine the flow of aquifer, so looking at the hydrology of the area, and then finally looking at the groundwater chemistry, so a more geochemical approach, and doing some analysis on that. And so from that we have some conclusions and some good reflection that we'd like to share, and we have some wonderful ideas for future projects, because like all science, it's ever going. So yeah, with that.
Thank you, Gordon. Okay, so to start, we're just going to give a little bit of background on the regional geology and the later step of more local geology. So as many of you probably know, Oakridge is located inside the Western Cascades, bordering on the Hydro Cascades right here. And generally we can zone these two apart from each other. The Western Cascades are a lot older, about 30 million years on average, and as such they've had a lot more time to weather. So that means that you're going to see a lot more like river channels carving down these mountains, and more time for the rocks to be weathered into things like clay. And clay is very important, especially for aquifers. Clay acts as an aquitard, which means that it's going to stop the flow of water. So what you have here in the Western Cascades is all these clays in the hills going into these alluvial aquifers, which kind of can block water flow. And that also means that just up in the hills, you're going to have a lot less water penetration. So there's not as much aquifer recharge going on. Now compare that to the high Cascades, which are only about 2 million years old, so much, much younger. You're going to have a lot more fresh, permeable volcanic rock. And this volcanic rock, because it's so permeable, allows for a lot more recharge. And this is where most of the aquifers that are underground are recharged up in the high Cascades. And one other thing that's very important, especially for Oakridge, is this fault running through the middle. So this is the Eugene Diener Fault. It's part of the larger Brothers Fault Zone, which runs from northern Nevada up through the Pacific Northwest. And there's a few different faults along here. There's one down here and one up here. But basically, this fault acts as a weak zone through the Cascades. Now, you all know that water likes to take its easiest path down, and that happens to be this fault because rocks sliding against each other is going to create a zone of weakness. And as such, you have the Willamette River coming through here and basically just following that fault line. And this is where we have a lot of our alluvial aquifers.
And now for the local site geology, here we have just a map overview of Oakridge. As you all know, the city of Oakridge is located in the central portion of the Western Cascades within the Willamette National Forest, about 35 miles southeast of Eugene, which is where we're all from. It is located within an alluvial valley, which is created by the deposition of sediments along rivers and streams over time. It is surrounded by highlands that are heavily forested with ridges as well. The surface drainage patterns in the area run from east to west through the two forks of the Willamette, Salmon Creek, and Salt Creek drainage basins. And lastly, the 4 major geologic units in the area are Little Butte Volcanics and Intrusive Andesite, which are the older volcanic rocks in the area, and then Glacial Outwash and Alluvium, which are the younger deposits. And these deposits are heterogeneous and consist of interbedded layers of sand, silt, and gravel.
So, just as an overview of how the water cycle happens in this watershed and in the Cascades, we can start off in the high Cascades where our tall peaks like Diamond Peak, Mount Jefferson, Mount Hood, all of our tall mountains, our youngest mountains that are at about 6,000 feet above sea level on average. And in this high Cascade area, they receive a bunch of snow accumulation in the winter months where snow is able to create snowpack, which then in the spring and summer months then melts and starts to recharge our aquifers that move down into our Western Cascade area. In our Western Cascades, we have the city of Oakridge, which both has surface water processes and groundwater processes, which we are interested in. And these surface water processes can be vulnerable to floods and rapid runoff due to storm events where there is rain on snow events or heavy rain events. And if there's a bunch of clay, like we have discussed, it makes it hard for that water to penetrate through and will result in flooding. Also in the Western Cascades, there are sustained base flows of water that happen through our aquifers that comes from our snow melt in the spring and summer months and allows for this sustained base flow throughout the summer months. And as that water moves all the way down to the Willamette Valley, into the valley floor, that is sitting at an average of 400 feet above sea level in our alluvial floodplain, there's a lot more groundwater and surface water interaction where chemicals in these waters are mixing in this low floodplain.
So kind of looking at the water cycle at a more local scale here in Oakridge, I've made this map here, and that kind of tan area shows what we're referring to as the Alluvial Aquifer. You can see it kind of starts and it follows down through, I believe that's Salmon Creek and then Mill Fork there. And it's kind of made of 2 main parts. There's what we call the alluvium, which is the river deposits which sit on top, and then the rest of that is kind of the glacial outwash from melting glaciers in the past. And here within Oakridge, most of the recharge, kind of zooming away from the high Cascades, obviously precipitation is a really big thing here in Oregon. About 45.41 inches per year here in Oakridge of just rain. Snowfall locally, about 3 inches, not as much as the high Cascades. So the snow melt doesn't really happen here in Oakridge. It's mostly up in the high Cascades and it flows down. It peaks in the winter, as you might imagine. It all kind of flows down and collects in that area, as you can see. And it's a primary source of drinking water for a lot of the residents here. I believe right in here is where the city's well field is. So a lot of the city water comes out of this aquifer. And the groundwater kind of moving through here because it's sort of an intermediate step in the watershed. It discharges to local lakes and rivers, which makes it really significant for recreation, fishing, swimming, all sorts of things like that. So within here in Oakridge, it is like the biggest player of the hydrologic cycle.
So I'm going to be talking about the methods and approaches we took to completing this project. The main question we investigated is how does groundwater flow within the alluvial aquifer system? So in order to investigate this question, we used 3 main scientific methods. Our first method was geophysical, so we used the GPR card. That's the thing you guys saw splashing around. And that helped us understand the aquifer lithiology and water table level. We then used hydrogeology to understand the hydrogeologic features of the aquifer system using pumping test data that give us values of transitivity and hydraulic conductivity, which will be further discussed later on in the presentation. Finally, we used groundwater chemical analysis to really try and understand the interactions of the groundwater within the system.
All right, so the ground penetrating radar, or GPR, was vital in determining the water level and also the general structure of the aquifer. And the GPR that we used was this 100 megahertz, it's called a Noggin 100. And essentially how it works is it shoots down radio waves, which then reflect off of subsurface features like clay lenses or boulders or the water table, which then goes back up to the GPR, and the time it takes for that radio wave to reflect back can give us a general understanding of how deep that feature is. And the GPR was also equipped with a GPS, which allowed us to get really precise depth measurements down to the centimeter. And the 100 megahertz allowed us to penetrate very deep into the ground with these readings, down to about 200 feet.
And then to use the GPR cart, we broke the city up into 3 different sections and then drew an individual transect line within each section that we ran the GPR cart across. So our first transect line was drawn next to the Willamette Fish Hatchery and adjacent to the butte. The second transect line we drew was next to the Public Works well field and along Sandy Creek River. And then the third transect line we drew was on the far western edge of the city. These transect lines were drawn with supporting data from the well tests that we got around the area.
All right, and so this is the data we collected from those GPRs. These are those transects. These are like cross sections. The blue is the water table, while the red is the alluvial deposits, so like sand and gravel and boulders and silt. As you can see, the water table generally sits at around 20 to 25 feet below the surface. And also of note is that it follows the surface topography. So like if the elevation were to increase on like a hill or something, the water table would follow. This was expected, and the 20 to 25 foot water table was also seen in the well logs. However, more extensive GPR mapping would be necessary in order to understand the field flow, or rather the flow field of the alluvial aquifer.
Alright, after we did the GPR and got to know where like the water table was and the shape of it, we next want to know these two hydraulic properties of the aquifer. And to do that, we do a pumping test. And here, I'll explain it right here how it's done. So for like a long period of time, water is pumped from a well, and what happens is like the suction creates a drawdown. The water level drops right around the well, and depending on how easily the water is able to flow through the ground, there's this cone. And if it's able to flow really easily, it'll just flow right up to the static water level where it's at. Like that's what we saw in the GPR. The straight line is the static water level. So we measure the distance on how much it draws down in the well to determine the transmissivity, which is just how well water can flow through an aquifer from the top to the bottom. And then with that, we can take the hydraulic conductivity, which is just how easily water is able to flow through that specific material. So we did our pumping test at the Oakridge Municipal Well Field at the well number 2. It's sitting right there, and the test was conducted on September 3rd, 2025. It's an automatic test that happens regularly. So here's the raw data. This is a graph showing the water level above the pump in the well, and this is time, so you can see it lasts a whole day. And each of these times where it drops down is when the pumping happens, and then stops, they let it return, and drops down again. And these are values for how much the flow is being pumped out. And using that data, we can calculate the transmissivity, which is 10,000 plus or minus 7,000 gallons per day per foot. And using that, we got the hydraulic conductivity, which is these figures here, but the 5.4 times 10 to the -3 centimeters per second is around what we expected it to be with a well-sorted gravel, even though it's a little bit on the slower end. So this is a data from the 1993 Oakridge Wellfield report, and you can see there's a bunch of tests conducted back then, like 30 plus years ago, and you can see the transmissivity values are way higher than what they are now. So the cause of that could either be that there's sediment in the pump screens blocking flow, or that there's just less water in the aquifer now compared to back then.
So the next part of our research focused on analyzing the groundwater chemistry in 2 different sites across the aquifer. Our goal was to see how the chemistry changes from one end to another, and what these changes mean in terms of water quality and how the groundwater is interacting with the underlying geology. All of our testing was done in accordance with US Geological Survey set standards. And off to the right there, we began by purging the wells. So essentially it ensures that we get all the old standing still water out of the borehole so that we can take our samples with the fresh aquifer water. We also followed protocol and made sure we were wearing gloves and avoided any sort of cross-contamination with our chemical reagents when we were testing. And by analyzing the chemistry, it allowed us to kind of track these chemical reactions. So this redox ladder over here, we started out by just testing general parameters, which include pH, temperature, and specific conductivity. And then these redox active agents or compounds we tested were manganese, ferrous iron, and sulfide. So this ladder essentially shows kind of how the microbes consume and reduce these oxidizing agents, starting with oxygen, and then they start to consume nitrates, and then down into the manganese. And so this continues down, and it kind of gives us some insight into what's happening and what this redox potential reading means. So our results we found were quite interesting, so I'll turn it over to Mia, who will get into our data and sort of what that means for the aquifer.
Awesome. So first I want to just kind of point out where our sites were. So we had Site E, which is right off TV View, right next to the fish hatchery. And then we had Site W, which is on the other side of town, more firmly within the middle of the Alluvial Aquifer. The reason that we wanted to do these sites in particular was because we wanted to kind of differentiate and see the alluvial aquifer by itself and an area that is closer to TV View, and just how those are different or similar. And as you can see, they're pretty different. So the pH increased by over 1, which is quite a substantial amount. The redox potential decreased substantially. The conductivity, which indicates salinity, nearly doubled. And then we have our manganese, which was more detectable in site W, which also lines up with the lower redox potential as we saw on the redox ladder. And then the ferrous iron and sulfide were more detectable at site E, which also lines up with the lower redox potential. So, the pH makes sense with our kind of ideas because TV butte is much younger than the surrounding area. It is much more prone to weathering and weathers a lot quicker. So silicate weathering causes a pH increase in groundwater, which is why we would expect for this value to increase. Also, our conductivity value, an increase in that value just means there's more like salts and maybe metals in the water, which also once again makes sense if it's interacting with TV butte and all of the weathering and stuff that goes on with that. So, the implications for this. First, we want to look at these cross sections. So this is the cross section at site W, which again is more firmly in the alluvial aquifer. And this cross section is very rough. But as you can see, there's no topography in here. So all of the groundwater is flowing east to west or out the screen at you. However, at site E, we can see that, as stated before, groundwater tends to follow topography. So we can see that the lines coming down from the butte indicate the groundwater flow, which would follow topography. As you can see, this arrow is going into the aquifer. And so what we found based on our data is that there is mingling from groundwater under TV butte and groundwater in the alluvial aquifer. And we know this because of the higher pH and higher salinity, which indicate that groundwater from under TV butte is mixing, as well as our redox potential readings, which differ across the city. So yeah, that's kind of the main takeaway from this. And then, thank you. Finally, so some conclusions just about the project in and of itself. GPR results were very valuable in mapping out the shape and composition of the aquifer. It also helped us find the location of the water table. Pumping tests revealed lower transmissivity than 30 years ago by quite a substantial amount. And finally, groundwater chemistry testing suggests that there is mixing between the alluvial aquifer and the water under TV butte.
So as with all science and data collection, we had some challenges, but we also had some really great breakthroughs. So first of all, collecting data with the GPR was trial and error. The early attempts that we had with it revealed limitations in both the techniques and the equipment settings, but we adapted. We went out into the field an extra day and we pulled the cart really slow, and we had a lot more stacking going on, so we got those really nice crisp images of the water table. We optimized the settings and techniques for better resolution and deeper subsurface penetration. And then in post, we discussed techniques to enhance the data clarity. And so, lesson learned, field science demands persistence, adaptability, and hands-on approach to problem solving, which didn't work well. So what comes next? So in the future, we would love to sample some more wells. Testing more wells means more data, which means more robust results. We would love to test the water chemicals for anions and trace elements. We would also love to do more GPR. We would love to learn where the water table is throughout the valley and potentially through the highlands. We want to see how the water table change and the flow direction of the aquifer, and more bedrock and alluvial aquifer interaction. And all of those lead into flow field studies as a whole. So we could discuss and look at seasonal fluctuation, seeing that the water table is lower in the summer and higher in the winter due to different levels of precipitation. We can see the potential long-term decline of the water table as we do further pumping and recharge throughout time. And then we would see how the flow field responds in the future, as more well pumping could result in a falling water table and evidence between the aquifers, like the alteration between the two of them. And then I get the joy and honor of giving all of the big thank yous. So first of all, we would like to say a big thank you to the EarthScope Primary Instrument Center for letting us use the GPR. It was a wonderful experience. We would like to thank the UO Sustainable City Year Program. We would also love to thank the USGS Eugene office, the Willamette Fish Hatchery, the Luga Lab for the University of Oregon's Biology Department, the University of Oregon's Department of Earth Sciences, and finally, an extra special thank you to you, the City of Oakridge. This would not be possible without you, so thank you very much. And with that, I get to invite Gordon back up and open the floor for questions, comments, and everything in between. Thank you.
I want to add one more quick thank you to the Oakridge Air for supplying us some wonderful masks when it was horrible. Yeah, so I'm happy to take questions, which I'm going to mostly defer, but yes.
Just wanted to make sure I heard this correctly. So the transmissivity now is way higher than it used to be, or way lower?
Way lower.
Way lower, okay.
Yeah, it was like, if you can go back to the slide and with the old table, yeah, right there. Those numbers you see are like from 26 to 85,000, and we got it at like 10,000 plus or minus a few thousand.
Wow.
Is that test done like around the same time of year, or is that like a more of an annual scale, or?
I don't know, Julie might know, he was the one that went to the public waterworks to get the data.
So the data was connected the week we were working here, so during these days. And if you look at this table, so there is number 5. If you can see what number 5, one of the tests in September. Oh no, it's September data. Oh, there's November, the data here was connected during the rainy season, which supposedly the more water is, and the data we connected was in September, which is the low water. So that might be reflecting part of the seasonal fluctuation. But throughout the state of Oregon, we do see the continual decline of groundwater water table throughout the Willamette Valley. So it is observation to be further confirmed, or conclusion to be further confirmed, that we suspect that the transmissivity today is smaller than 30 years ago. Now, one question as you raised, that is, our test is done in September, which is during the dry season. And this historical data was done during the rainy season. So possibly they should be high, but is it that high?
Yeah.
I'm not sure. But we can, so to be further explored.
Gotcha.
Because I do recall Robert Chrisman, our public works director, has been here for 25 years. He had said, for sure, in his 25 years here, he's noticed it dropping a lot. And our residents noticed because the water is cloudy, because it's sucking in a lot of air.
Yeah.
And yeah, citizens are concerned about it. It is just air, so it's safe to drink, but he's definitely seen the level of water drop significantly over 25 years. So, yeah. Thank you. So there was another possibility. It was either less water in the aquifer more, did you say like more sediment, or that's the wrong word?
The screens.
Yeah.
Screen.
So we were asking Robert.
Well, they actually were just, I think, got the new screens.
Just 3. They tested well 2. They actually replaced the screens on well 3. So that was another question is that, and these numbers are for wells 5 and 6.
Which are fairly close.
Which what?
Fairly close.
To the
where we
same
tested,
spot.
Yeah.
So that, I guess the concern would be the sediment, if
Yeah.
it's stuck in the screen, probably worth the test on well 3, which was just refurbished. Would be a nice step.
Yeah.
Yes.
I have a question about water flows from the butte. I just want to make sure, like, my understanding of things is accurate in this. So, since it does show that our aquifer can be directly impacted by, the water flow coming from PV Butte, if there was any major impacts to the butte, would it be safe to say that that could ultimately impact the chemical makeup in our own city's aquifer that could create impacts on our water quality?
So, I think that we would definitely have to do more testing, and one thing we do know about the bedrock or the volcanic rock is that water does travel slower through the volcanic rock than it does through the alluvial aquifer. But I definitely think that, as we saw, there is mixing, and so given enough time, if there is contamination, it definitely has the potential to mix into the aquifer, but once again, we need to do more testing, I think, to be 1,000% sure.
So if they did do, like if there was impacts to the volcanic rock that was on the butte, that could ultimately impact things even more so, since that would impact a slower moving water. If you were to remove that rock or disturb that rock to make way to other areas, I hope this is making sense. Would that impact?
Yeah,
could impact it even
I
more so?
understand, what you're trying to get at there. So without further testing,
Yeah.
basically our preliminary results kind of showed, and if you can go back to the results section. So typically, when we have, I guess the conductivity was a big one, because usually from east to west, if you're in the same system, same aquifer, we would expect that over time, your conductivity, like on the western portion, would be higher because the water has more time to kind of dissolve and build up more metals. But you can see in sight on the eastern site right near the butte, those levels are almost double, which kind of shows some evidence that there is water interacting from the butte with the aquifer. So, again, more testing and more well testing around the butte, maybe some wells in that area would help make that link a little bit stronger. But there's definitely, we found probably some connection between the butte area and aquifer and what's going on there, and the alluvial aquifer that the residents use for drinking water.
Gotcha. And is that to say that the same thing could be kind of said that with the flow, since it goes through Salmon Creek and the Willamette River, it could also impact the chemical makeup in those areas as well, correct?
I would think, as the water is moving from east to west and passing through those areas, passing through the butte, we can, by testing wells, you could probably see how far and how extensive some of that intermixing would be.
And another one, looking at the GPR data for Garden Road and then the other areas, it seemed like it was a lot deeper in Garden, the aquifer went much deeper. Is that true reading of that, or is that a problem with GPR?
Here's how this works. So, you have to walk really slowly.
Yeah.
And if you do not walk slow enough, occasionally there could be interference. So what's likely happening is all that darker blue underneath the water table is not actually representative of what's there.
Again.
It could also be Garden Road was along the Willamette though. Right?
There's
West
a-
to south. Their transect is running essentially
North-south?
No, that's east-west, or no.
So-
North-south.
If I can interject too, that when we're walking, we have a screen, and if we go too fast, it'll give us a little blip.
Yeah,
And those blips certainly aligned.
with what you saw.
So that was a bit of trial and error, and we got some decent transects. But again, we would love to really be able to come back and do a further assessment.
So that transect is also connected in the afternoon when we were tired and really wanted to go home, just to finish it and go home.
I have a question regarding, the amount of water available. So since there is, evidence of not being as much water, is it, or should we do more study on this kind of thing? If, say, somebody was to try and create their own well somewhere around the Butte, around TD Butte, and try to pull like 5,000 gallons a day, what kind of impact would you guys say would have on our city's aquifer?
We do need to do more tests in order to really fully understand the availability of the water. This is a good baseline preliminary assessment, so it's difficult to say. Yes.
I was wondering if somebody could point out to me on the geologic map where TVB is.
Oh, okay.
It's over there.
I'm going to say as a caveat right now, these geologic maps are
Really old.
well. So I think
More than the
It's-
geologic map.
actual.
Chewy, could you
Chewy,
go
one
to
more.
the local site geology one? I think they were just
Yeah.
a better.
Yeah, that's
No,
perfect.
that's
You can see it.
topography. I want the geology.
One more tree, please. So it would occur right around here, and
Would
the
it
I mean,
issue.
what they have mapped
Would
is
it
a
not be the
copy.
yellow?
Which is, yes, so the caveat with these maps is these are
Much like.
digitized in much larger scale, and so this does not give a perfect representation, and so these, at least like, these are two actual like 20-foot plots.
Sure.
And so, yeah, so it's done at a much bigger scale and it's not perfectly mapped, but
My other question is like, how exactly does the geology of Butte affect what you guys are getting in the readings?
Yeah, I mean, the geology really has a lot to do with what kind of readings we're getting. And as Gordon said, this map is not the greatest. There was one other USGS study from, I think, Willamette Pass, when they were trying to get some stuff done up there. They had some mapping done. And TV Butte and the related stuff over here was found to be much younger geologically, more in line with High Cascades age, about 2 million years old. And as I was saying at the beginning of the presentation, that means that you're going to have a lot higher weathering rates because that's a lot younger rocks. So you're going to end up with what we essentially saw with higher content of metals and such.
Is it basalt then, Butte, or is it
It's
like an
andesite,
Yeah.
yeah. But it's distinct from the rest of the Western Cascades that surround this Oakridge. So, yeah.
Were you guys able to tap into the geothermal study that was done here as well, and trying to at least make some comparable analyses of what you did?
I looked a little bit at that. You're talking about the one by the hot springs, correct?
It was kind of a part of this whole area, and I think it's actually connected to the other study you were referencing around Willamette Pass. A bunch of stuff was done, like early 80s.
Started in 1979, actually.
Yeah.
Typewritten.
Yeah.
So, I will say, maybe, we ended up looking through a lot of those well reports, and so there is a variety of different information sources. We didn't look specifically at the hydrothermal studies that have been done.
Yeah, I was just curious because the wells themselves are like in this area, and if you located the wells, I want to know where
We spent a good deal trying to actually figure out where the addresses are of all of the individual wells so that we could try to cross-reference all of our data. And so we did our best, but again, I'm not sure how many of those specific ones we were able to locate or not.
Donnie doesn't have useful information on it, so that's.
Yeah, so I can talk more to this
Yes.
later because I think that I might lose some people, but I'm happy to discuss a little bit later. Yeah.
So one more, just so I can better understand the pump test. So when you get that, so it's caving, not caving, but the down.
Depression.
Yeah, the depressions. Does it mean that, could it mean that the ground is not as porous as it was? Or is it always indicate a lower water level?
I think it would be hard to say that the ground changed like porosity because I mean the sediments are so like packed in there that unless they're like flooded out and like the whole everything was like broken open, I don't think it would really change. I think as the water flows, it's like I don't know. I think of it as if you're like drinking out of a cup with a straw.
Yeah.
If there's nothing in the cup, then the water just drops flat. But if you have a bunch of stuff in it, then the water around the straw will drop. It's like more and more.
Okay,
Yeah.
I get it.
It's like it's so weird.
When is this study planning to be published? Roughly.
It's a great question. We are hoping to continue on and have more on it. We're working on putting together a little website, so we'll keep you posted.
Is the preliminary part of it, will it be available?
Yeah, we'll make that available.
Awesome.
I have one more thing about the geothermal stuff. I believe it was the same study that we read in Earth Physics. Maybe it was a geothermal study using wells in the Western Cascades, and they had to drill really, really deep to even like get barely any heat. So there's like nothing we would be able to realize with our equipment during this.
Is there a way to estimate what was it called, groundwater discharge to the rivers and ponds?
There is. Again, we need to do a little bit more, but with some of our data, we should. I think we need a little bit more, but we can estimate it roughly.
Sure.
Yeah, and I think that that's also another part to it, that we need to look at seasonal variations during the dry season. It might actually be leaking the streams, whereas during the wet season, you might be adding to the streams. So, any other questions? Yes.
How did you all like the work?
Beautiful job, very well presented, thank you. Russ, Thomas was very well presented, yeah. Appreciate it.
Well, thank you very much, everyone, for your attention. The lively discussion.
Yeah, on behalf of the city, thank you very much.
Yes, thank you so much. Great, we appreciate it.